Hello! In this video, we will discuss the existence and uniqueness of first-order equations. Existence and uniqueness are two important topics in differential equations. So when it comes to existence, what we mean is, does a solution to the differential equation exist? And uniqueness is the solution unique? So it turns out that there are theorems in each of the types of differential equations that we're going to look at throughout this course, which will discuss these two factors before you even solve a differential equation. So you can just look at a differential equation and be able to determine, is a solution likely to exist, and is that solution likely to be unique? So that's a very good quality, right? Because if you're looking to solve a differential equation, it would be nice to know before you begin that it does have a solution, that a solution does exist. And then if you solve a differential equation, it would be nice to know that there are no other solutions, that you've found the only solution that does exist, that your solution is unique. Okay, so the theorems in this section specifically are first theorem we're going to look at is the existence / uniqueness of linear first order equations. Okay, and here is what the theorem says. If the functions p and g, which you'll see where those come from in a second, p and g are continuous, on an open interval I, which is defined to be alpha less than t less than beta, containing the initial condition, the initial point, t equals t naught, then there exists a unique solution y equals phi of t that satisfies the differential equation y prime plus p of t y equals g of t for each t in I, and that satisfies the initial condition. Y of t naught equals y naught. Okay, so there's our theorem. And let's just spend a second and study it. What does this theorem say? Okay, so if you go through and you read it carefully, if P and G are continuous on an open interval containing the initial point, right, basically the initial condition, then there exists a unique solution that satisfies the differential equation and the initial condition. Okay, so what did we get in there? We got exists, unique. Okay, so there's two things that are in there. So what does this theorem say? It says that if P and G are continuous, then we get existence and uniqueness. That's the short version, right? And in particular, what are they continuous on? They're continuous on an open interval. So we have to have some region where they're continuous. If they're continuous on a region, then we're guaranteed to have a unique solution in that region. And that's the major part of it. The one other thing here that maybe you could pull out, right? So the important stuff is if P and G are continuous, that's obviously critical. Open interval I, so we've got an interval, right? There exists a unique solution for each t in I. So this is also something that you could pull out that is relatively important. So there exists a unique solution for each t in I. So as long as the initial point is inside of the interval, then at every point in the interval, there's guaranteed to be a unique solution. So not just one, but at every point. Okay, so that's a stronger statement, right? As opposed to just saying that there exists a unique solution that's in the interval. Okay, so that's really what you end up getting out of the theorem, is that if P and G are continuous, then you get existence and uniqueness. And then as a bonus, we get that there are solutions for each t in I. For every t in I, we're going to get an existing unique solution. Okay. Well, what else do we want to say about this theorem? Why would this theorem be true? So we aren't going to go through and formally prove this, but if we think about it, we can go through and explore it using the information that we've already covered in previous videos. So first of all, take a look at the format here. Right, what does that format look like? That's our general first order, our general linear first order differential equation. That's the same format that we used in going through and solving problems using a integrating factor, right? So those are the integrating factor problems. Right? And so recall, how did we solve integrating factor problems? Right? First, we go through and we find the integrating factor itself, mu of t, it's equal to e to the integral p of t dt, step one. And step two, you get y equals 1 over that mu of t times the integral of mu of t g of t dt plus c. Okay, so it's a two-step process in order to go through and solve one of these integrating factor technique problems. Okay, and if you look at those, look at what we need to be able to do to solve that. So we need to be able to integrate p of t, and we need to be able to integrate mu of t times g of t. And the question becomes, what type of conditions would we have to have on p of t, mu of t, and g of t to be able to integrate them and end up getting a nice solution, a solution that's well behaved? And that condition is going to be continuity. Okay, if you have a function that's continuous, all right, if p is continuous, then you know that the integral of p is also going to be continuous. You're guaranteed. So if you have continuity of your function and then you integrate it, you're guaranteed to get continuity of the resulting function. And so you could think of continuity, the way that you could interpret it, it's kind of like it's like kind of like asking, does a function behave itself? Is it well behaved? Does it handle integration and differentiation? Does it handle those processes well? That's why we go through, and you regularly see in calculus courses, conditions on functions when it comes to differentiation and integration regarding continuity. It's because continuity is this catch-all term for, does it behave itself, right? And if you're familiar with calculus 1 and you know what discontinuities are, so we're looking for functions that if they don't have asymptotes, okay, um, they don't have jumps, right? They don't have holes, like they don't have these things that would create problems when it comes to integration or differentiation. Now, of course, we could have a function in here that does have an asymptote, but then we would want to ensure that t is not, we're not plugging t in where that asymptote is. Okay, so anyway, this is just a long preamble to say that if these things that are inside the integral are continuous, then we're guaranteed to get nicely defined results. So that's the way that you could interpret that, right? So, and what are those? So p of t needs to be continuous. And mu of t, of course, which is the result of integrating p of t. So if p of t is continuous, then that mu of t just inherits it. And then g of t, right? And so that's where you can go through and kind of, explore the theorem and come up with, what the thinking is, right? And that is that if p and g are continuous, then if you have this problem, right? If p and g are continuous and you have this problem, then what you can do is you say, all right, I've got my problem here. Let me go ahead and use my technique, my integrating factor technique. What does my integrating factor technique force me to do? Well, it forces me to integrate p. Well, if p is continuous, I'm guaranteed to get a nice mu. If I've got a nice mu of t that's continuous and g of t is also continuous, then I'm guaranteed to get a nice continuous result from this integral, and then I'm guaranteed to get a nice solution from y. And it's just this chain reaction of ensuring that if you've got continuity, then you get continuous results, which allows you to continue forward and keep integrating and get to the solution. Okay, and so that's the basic idea behind the theorem. Okay, but one thing that I do want to be clear here, and that is that if P and G, if P or G, right, if P or G is not continuous, okay, then that doesn't really tell us anything. That doesn't really tell us much about the rest of the problem, right? So if P is not continuous, then is it possible to integrate it and end up getting something that is nicely defined that you could end up with for mu? Yes, it's possible. You can have functions that are discontinuous that if you go through and you integrate them, they become better behaved, okay, after integration. And the same thing is true here, but that's not the point of the theorem. The point of the theorem is what guarantees that you get nice behavior, and continuity is that thing. If you have continuity, then you're guaranteed to be able to go through and do all of this stuff and get a good answer, right? So the way that you could interpret this, right? So here we have the theorem, right? If P and G are continuous, then a unique solution is guaranteed to exist. Guaranteed. Nothing can go wrong. What the theorem does not say if P or G is not continuous, then a solution does not exist. Then a solution does not exist. Or the solution is not unique. So I want to be clear. The theorem does not say this. Okay, you cannot interpret that from the theorem. The theorem just says this. The theorem just talks about what conditions guarantee a solution. And so if you have continuity, then there's guaranteed that nothing can go wrong. If you do not have continuity, then the theorem doesn't tell you anything. Okay, you could have a solution that exists. You could have a solution that exists that's unique. You could have a solution not exist. You could have a solution exist that's not unique. Okay, anything is possible. And so the reason I wanted to touch on this briefly, right, is because this is something that if you're a student and you're new to theorems and proofs and other things like that, one of the things that's helpful is to learn some basic logic principles. Okay, so maybe P is not a good choice here, but this is the classic way of writing an implication. Okay, and that is that this is translated as if P, then Q. Right? If this is true, then this is guaranteed to be true. If P and G are continuous, then this Q is guaranteed to be true. The way that you would write this this situation here that I've got here is I've gone through and I've taken if P and G are continuous. The opposite of that is if P or G is not continuous. So you'd say that's not P, and then a solution does not exist or is not unique. That's the opposite of the solution does exist and is unique. That's not Q. Okay, this is the inverse of this. Right. If you go through and study a little bit of logic, this is the inverse. And so you could translate as if not P, then not Q. Okay, these are not equivalent. Okay, so if you have an implication, you cannot translate the implication into this inverse form. And so you just need to be careful about going through and reading a theorem and understanding what it says. Okay, so this theorem, right, if you go through and you read it carefully, it does not say this. It could not be twisted around into this. It is not equivalent to this. If P or G is not continuous, then it just says nothing. Okay, so anyway, you just need to be able to read theorems and be able to understand what they're talking about. Okay, so as far as using the theorem, what will you what is it a student expected to learn about or expected to use these theorems for? Well, we can go through and we can apply the theorem to find where solutions would be guaranteed to exist and be unique. Okay, so here's an example problem we can do. Use theorem 2.4.1. Oops, sorry, that's from the textbook we're using. Use the existence/uniqueness theorem to find an interval in which ty prime plus 2y equals 4t squared and y of 1 equals 2 has a unique solution. Okay, so you could break this down into a couple steps. The first step is we need to have the theorem in the proper, we need to have the differential equation in the proper format. So if you go back to the theorem, it has to look like this. So you need to go through and move things around until it looks like that. Right, to do that, so if you look back at that, the y prime is by itself, so you need to divide the t on both sides. So we'll end up getting y prime plus 2 over ty equals 4t. Okay, so that ends up being our format that matches with y prime plus p y equals g. And so that tells us that this is p and this is g. Okay. Oh, and then one other thing, you can go ahead and just take y of 1 equals 2. This is t naught, just to be clear, right? That's the initial point that we plug into our initial condition. Step 2, we need to go through and find the continuities. So we need the continuity of P. So what's the continuity of P? If this is P, all right, so continuity, this is a single variable function of T. So we're just go through and just talk about what conditions have to exist on T for this to be continuous. It would be T such that T is not equal to 0. All right, and then continuity of G. All right, so that's the continuity of 4t. What conditions are on 4t for this to be continuous? None, right? So t can be any real number. This symbol, if you haven't seen it before, just means as a member of. Okay, it just means t is a real number. It's another way of saying is. Okay, and then continuity. Now, here's the thing. So you've got these separately. What do we need? We need continuity from both. So this is the way you write it, P intersection G. Okay, if P has some continuity requirements and G has some continuity requirements, then we want to find the places where both are going to be continuous. Okay, now in this case, there's only one discontinuity, that's at 0, and so the intersection of the two, the combination of the two, is just going to be just that one. But it could be more complicated than that. Like, so for example, if P had been the, P is continuous where T is not 0, and G is continuous where T is not 1, then the intersection of the two is that T would be continuous where T is not 0 and T is not 1. Okay, that's how you could go through and combine them. Okay, and then step 3, what you can do if you wanted to go through and find the interval, right? Find an interval, all right, is you can go through and you can just draw a number line. I think this is the easiest way to do it. And then go ahead and put the places, the discontinuities, put the places where the function is not continuous on your number line. And so in this case, it's just 1, but if we'd had more, you could put more on here. And then once you've done that, what those discontinuities are going to do is they're going to break up the number line into regions that are continuous. So we know we've got continuous and our function is nicely defined, here, and we've got, continuity and the function is nicely defined here. So these are both regions over which we could go through and we could, integrate P and integrate mu and G if those were the conditions, right? So this tells us where we could go through and integrate and not have any problems, not have any trouble arise, where our function behaves itself. Okay, and so once you've gone through and you've taken your continuity of P and G, your intersection here, and you've just tossed it on your number line, then the last thing to do is you just take T naught and you put it onto your number line, right? So T naught is at 1, right? So here's 1, here's T naught. Okay, and so what you want to do is, where does the theorem determine that there is a unique solution? Well, it's the interval that's continuous. We've got a continuous interval here and a continuous interval here. It's the interval that's continuous that contains the initial condition. So this guy here is the interval that's both continuous and contains the initial condition, right? If you go back and maybe read the theorem, for the 3rd or 4th or 20th time, right? If the functions are continuous on an interval that contains the initial point, that's what we found, right? We found regions where the functions are continuous, and we found the one that contains the initial point. So that's going to be our answer. And so if we were giving our answer, use the existence and uniqueness theorem to find an interval in which we have a unique solution. That would be the interval T such that T is greater than 0. Right? That's what is highlighted here. That's that interval. Okay. Let's try a second example. A more complicated one. Find an interval where the solution is guaranteed to exist. And be unique. All right, so yeah, that's implied. All right, so natural log T y prime plus y equals cotangent of T, and we have y of 2 equals 3. All right, so step 1, we need to put it into the format, right? So what's the format? It's y prime plus py equals g. So it needs to look like this. Initially, it does not, right? We have y prime, it's not by itself. So you need to move that natural log T over. So we're going to get y prime plus 1 over natural log t y equals cotangent of t over natural log t. Okay, and so this is p, this is g. And we'll go ahead and throw our initial condition down here, write it again. This is t naught, right? As we discovered on the last problem, that does matter. Okay, so we need to go through and find continuity of p. Where is p continuous? Okay, so you need to think about this for a second, right? So the natural log function, where is it continuous? Okay, it's only defined, right, for values that are greater than 0. So we know that t has to be greater than 0. And then on top of that, since it's in the denominator here, it cannot be 0, right? If we have divide by 0, that would be undefined. And so what causes the natural log t to equal 0? It's t equals 1. So t has to be greater than 0, and t cannot equal 1. All right, how about continuity of g? So g has that same condition where natural log is in the denominator. So we can just kind of inherit those. We've already done those. Okay, and then we also have to, how about this cotangent, right? So if you recall that cotangent is 1 over tangent, if we think about where tangent is 0, right? Tangent is 0 at 0, pi, 2 pi, and so we could say that t is not equal, cannot equal pi k, where k is an integer, right? This is just another way of saying that t cannot be 0, pi, 2 pi, negative 2 pi, and so on. Okay, and then we need the intersection of these two, p intersect g, right? And since they overlap, it's just going to be basically everything that's up here. And the overlap is these two, so we know that's going to be in there. But the intersection, so it has to basically any conditions here that put limits on the on the interval where the function is continuous, those are going to exist on the intersection as well. So we're going to have t greater than 0 and t not equal to 1 and t not equal to pi k, where k is an integer. Okay, and then finally we can go through and do the number line. And if you go through and we have 0, let's put 0 on here. We have 1, and then we have multiples of pi. So if this is 0, this is 1, we'll say this is pi, this is 2 pi. Well, that's really not the scale, is it? I guess we need to move this a little further over. That's 2 pi. And it continues. 3 pi is way over here. Okay, so what this has done is, just like the first case, it's broken up the number line into regions that are continuous, regions where the functions are all well behaved, okay, where they behave themselves, and you'd be guaranteed to be able to integrate and find an antiderivative that's going to be nicely defined for, for mu. You'd be guaranteed to be able to integrate p, and then you'd be guaranteed to be able to integrate the result of mu times g. Okay, you'd be guaranteed to be able to go through and do all those integrals and not have any bad stuff happen, not have any shenanigans, right? So you have just this nice continuous functions. The integral of continuous functions are continuous; they're well behaved, and so these all give us regions. And so you can go through and say, all right, so this is a region where everything is nice and behaves itself. Here's a region, here's a region, and you could do another one from 2 pi all the way out here to 3 pi if you wanted, right? Don't go this way, right? Because we have this condition, t is greater than 0, right? So 0 is the lowest value. Okay, and then finally, the last thing that we do is we want to know which of these intervals contains the initial point, because that's part of the theorem, right? The theorem says we need to have continuity on an interval that contains the initial point. So that additional requirement. All right, so what do we've got? We've got y of 2, t naught is 2. So where is 2 in here? Well, if this is 0, this is 1. Well, it's clearly not in this interval. And then we've got 1 and then pi. Pi is about 3.14. So 2 would be between 1 and 3.14. So we'll just throw a little dash in there and say that's our t naught. And so that's our interval. Okay, and so t such that 1 is less than t is less than pi is going to be our interval where we're guaranteed to be able to go through and do our integration and not have any problems come up. Okay, so that's the first theorem, existence and uniqueness of linear first order equations. Let's look at another theorem. Theorem number 2. This is going to be existence / uniqueness for general first order. Okay. So what does this one say? So let the function f and partial of f with respect to y be continuous in some rectangle alpha less than t less than beta, gamma less than y less than delta, containing t naught, oops, about to put an x there, t naught, comma y naught. So let's just pause there before we go on. So far, the theorem is similar. Okay, now there are some differences. Notice how we have f and partial of f, and we haven't even defined what f it is yet, but we will before the theorem is done. But so we've got two things that need to be continuous. That's just like the first theorem. And then we have some interval. Now this time the interval is two-dimensional instead of one-dimensional, and that interval needs to contain the initial condition, or something that will be clear that's the initial condition once we write the rest. Okay, so far the theorem is quite similar in structure. And then you get a curveball. So then in some interval, t naught minus h less than t naught plus h contained in alpha less than t less than beta, there is a unique solution y equals phi of t of the initial value problem y prime equals f of ty and y of t naught equals y naught. Okay, so that last part makes clear what the f is. The f is the definition for the differential equation, right? So it's the definition for the derivative of y. And then it also makes clear the t naught y naught is the initial condition once you see it in this form. Okay, so but let's just be clear about what the difference is, and that is that you have this then in some interval piece. This is not in the first theorem. So what does that specifically say? So in the original theorem, if you had continuity in an interval, then you were guaranteed to have a unique solution. This time, if you have continuity on an interval, then some interval inside of that interval is guaranteed to have a unique solution. Okay, so just clear about that. That's what this is saying, that in some interval inside of alpha to beta, there is guaranteed to be a solution. Okay, so as far as, what does this theorem say? Right? If f and partial of f with respect to y are continuous, then a solution exists and it's unique. Right, almost. If they're continuous, right, then a solution exists and is unique. All right, somewhere inside where they're continuous, right? That's what we were just saying. For some interval inside where they're unique. Just add that. That's kind of the Cliff Notes version, is that if we've got continuity, then we've got a solution existing and being unique, but it's only for some area, for instance, some region inside of where it's defined to be continuous. Okay. All right, let's go through and look at an example. How could we go through and use this theorem? All right, so we're going to apply this theorem. Apply the theorem, the general first order theorem to the following initial value problem. We have dy dx equals 3x squared plus 4x plus 2 over, let's try that again. Over 2 times y minus 1. And they give us the initial condition, y of 0 equals negative 1. Okay, so the first step is very similar to the first step, and that is you want to compare what they gave you with the format from the theorem. So what does the format from the theorem say? It says that y prime equals f of ty. All right, so we've got y prime equals f of t comma y. So what does that tell us? Well, this is the same thing as y prime. And so it tells us that this thing is f of ty, or in this case, f of xy. Okay, And then second, we can use our initial condition, right? We've got y of t naught equals y of t naught equals y naught. To tell us that this is x naught and this is y naught. Okay, so step 2, once you have gone ahead and compared the given information to the theorem information, so you figured out what f is and you figured out what x naught and y naught are, then the second part of the problem is we need to go through and calculate the partial derivative, because we're going to need a partial that's in there, right? So we've got the partial of f with respect to y, so we need to go through and calculate that. So if we're going to differentiate this, so we're differentiating this with respect to y, that means we treat the x as a constant, so we keep 3x squared plus 4x plus 2, and then we're going to multiply by the derivative of this, oh, and then you could pull out the 2 as well, right? So over 2, and then we're just going to multiply by the derivative of this piece here. So this is y minus 1 to the negative 1, so we're going to get negative y minus 1 to the negative 2. Okay, and if you go ahead and recombine these, we're going to get negative 3x squared plus 4x plus 2 over 2 times y minus 1 squared. Okay, so now that we've done that, we can go through and figure out, we have to figure out continuity of f. What's f? This thing is f, right? So it's right there. F is this. And so where is this continuous? Now, one of the things about continuity here, because we have two variables, we're talking about continuity of x and y. So you need to look for restrictions that would exist for either of the two variables. So if we look at x is just this polynomial. So there's no restrictions on polynomials. Polynomials are continuous everywhere. They're very nicely behaved. And then as far as y is concerned, since y is in the denominator here, y cannot equal 1. All right, and then next we have to go through and find the continuity of the partial of f with respect to y. And you want to do the same thing, but use the partial result. So our partial derivative is given right here. So it's this guy. We still have the polynomial, so x is still without restriction. And y, although we differentiated, nothing changed, okay? Y still cannot be 1. And then finally, if we had something different between these, then this would be a little more interesting. But the intersection of these two, which is going to be, the we need to combine these in terms of going through and finding the places where both of them are continuous. They're both the same, so nothing changes. We get x is a real number and y is not 1. And then the next step, step 3, right, is to go through and kind of draw the number line. Now the equivalent is not to have a number line, right? If you look at the theorem, what does the theorem say about the interval? The theorem says a rectangle, right? So we've got 2 dimensions, right? So let's just take a look, right? So the theorem says let the function f and partial be continuous in some rectangle that has t and y, 2 variables, right, containing 2 variables, t naught and y naught. Okay, so that's the way that you handle that rectangle, is with 2 variables. And so we're going to have y, right, is here, and x is here. And so in terms of translating this, the places we've replaced t with x. Okay, so t would normally be this horizontal axis. In this case, we're using x because we've replaced t with x. Okay, and so next, what you need to do is you need to go through and draw the restrictions here. Okay, so x has no restriction. So if something is unrestricted, then you don't draw anything. Y cannot be 1. So you want to go to 1, and y cannot be 1. Well, that's just a horizontal line, Y equals 1 is just a horizontal line, and not being 1 is just not being that horizontal line. Okay, and so if you go through and do that, so there's the restrictions. We've graphed them now. What you'll see is you get two pieces, like this and this, right? And these do extend, of course. I'm just circling just the parts that we can see. I'm going through and I'm trying to represent the equivalent of these parentheses, for that we did for the number line. So that's what these boxes are. They extend in every direction here. And so the question is which of these two boxes are we guaranteed to have a unique solution, right? So what do we have to have? We have to have, if we go to the theorem, we have to have f and partial of f be continuous, and they have to contain the initial condition. So which of these, so here's our regions where we have continuous. Now, which of them contains the initial condition? Well, let's just take the initial condition and graph it on here. So y of 0, so it's saying x naught is 0, right? So x naught is 0, that's right here on that's the y-axis. And then y naught is -1. And so, wait, hold on. What happened? Oh, yeah, I got it. The dashed line is 1. All right, now don't lose track of what is what. I was thinking the dashed line was where y was 0. I was like, hold on, something's wrong. And so, yeah, there's 1. And so y is -1 would be down here. Okay, and so this would end up being our answer. Okay, so if you were to go through and give your answer, where are we guaranteed? Well, hold on. Let's qualify that. So we have x and y, where, right? So what's the condition here? So x could be anything, and y has to be less than 1. Right? That's the box that contains the initial condition. Now, what are we guaranteed? We're guaranteed that some subinterval of this, right? So some subinterval, that's the second question, this weird qualifying second condition here, is that some interval inside of that is guaranteed to have a solution. So somewhere inside of there, we are guaranteed to have a solution. And that's how the theorem works. Okay. So the general first order theorem, which is the one that we're looking at now, right? So this is the general first order equation theorem, whereas the first one we did was the linear first order equation theorem. The general one is applied this way, okay, as compared to the linear. Okay. All right, so there's one other thing before we move on that I did want to discuss with this problem. And that is, so, right, the initial condition could have been anything here. It didn't have to be y of 0 equals -1. We could have put anything. What if we'd made the initial condition, what if we'd caused the initial condition to land on this dashed line? What happens? Okay, what if the initial condition had been y of 0 equals 1, right? What would have happened then? Okay, so you've gone through and you have done all this stuff, and then we would have gotten to here and we've said, oh, hold on, the initial condition is right on the line. So because of that, we would not have been able to use the theorem. The theorem would not have been true. All right, there would not have been a f and partial of f that are continuous that contain t naught y naught. That would not have been possible because of the fact that the initial condition t naught y naught lands on the place where there is a discontinuity. Okay, so that can happen. What happens if you go ahead and just solve the problem anywhere, even though the theorem does not apply? Okay, well, if the theorem does not apply, any outcome is still possible, right? You could go through and you could still get a solution. You could still get a solution that's unique. Anything is possible. So it's just like the first case that we were talking about, right? This does not say if f and partial of f, are not continuous, in a point that contains t naught, y naught. That doesn't say that then there is not a unique solution. It doesn't say that. You cannot go through and infer the inverse. Okay. That said, if you go ahead and you have y of 0 equals 1 and you go ahead and solve it, then something neat does kind of happen. Okay, if you go through and solve that, so what if the initial condition, so you can go ahead and try and solve that. What you'll end up getting is you'll end up getting that y equals 1 plus or minus the square root of x cubed plus 2x squared plus 2x. This is the solution that you'll get. Now, and this is taking into account that you use the initial condition to get rid of the c. Notice the c is gone. So we've used the initial condition to get rid of the c, and this is what we end up with as our solution to the differential equation. Now take a look at that solution. Do you see any problem with that solution? Okay, is that a good solution to a differential equation? Well, one issue with it is this plus or minus. The solution is not unique. There are two solutions. That's not good. We like to have only one solution to our differential equations. So in this particular case, when the theorem did not apply, where we could not find a region where f and partial of f were continuous that contained t naught, y naught, then the outcome was that we did get a solution, but it was not unique. Okay, so that's not guaranteed though. Okay, just to be clear, that similar to the first case, you cannot infer the inverse. Okay, it's possible that you could have f and partial of f not be, that there not be a region where they're continuous that contains the initial condition and yet still have any possible outcome. Okay, let's look at one more example. Find where in the ty plane the general existence uniqueness theorem is satisfied, and the differential equation is dy dt equals cotangent of t divided by 1 plus y times y. Okay, so step one, we want to compare this. So the theorem says y prime equals f of t comma y. So if you compare these two, this is y prime. And so it tells us that this thing is f of ty, right? So we need to identify what f of ty is. All right, now there is no initial condition because they're basically just going through and throwing out a general question where could we go through and have continuous regions where we could put initial conditions. So they're not specifying an initial condition. Okay, so step two, we need continuity. Oh, I skipped a step there. We need to go through and find the partial derivative. All right, so first go ahead and find partial of f with respect to y. So if we differentiate this with respect to y, what you can do is you can, you treat t as a constant, so just move the move the cotangent of t off to the side, and then we need to differentiate what's left here, this y over 1 plus y. And to do that, that's a quotient, so we can use the quotient rule. We get the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. So we end up with cotangent of t times, we've got 1 plus y minus y, so that's going to leave us with 1 over 1 plus y squared. Okay, so once we've gone through and found our partial, we can calculate the continuity of f. So that's this original. All right, so where would that be continuous? And we need to think in terms of t's and y's. All right, so we can see easily enough that y cannot be -1. And then also, I guess we should put an and here, not a comma. And what about t, right? So this is, again, cotangent. We discussed cotangent earlier. So cotangent is 1 over tangent, and tangent is 0 at 0, pi, 2 pi, so on. So we want to say that t cannot equal pi k, where k is an integer. All right, what about continuity of the partial of f with respect to y? And we take a look at that. We still have that cotangent in there. While the derivative has changed this second part here, we still have 1 plus y in the denominator. So it's the same. It's the same. Let's just put same. Okay, and then continuity of the intersection of the two, f intersection partial of f. That's also the same. Okay, all of these are the same. All right, and then as far as to go through and draw the picture so we can find the regions. So what's that going to look like? So we're saying that y cannot be -1. Okay, so let's go ahead and on here, let's put a dash line there at -1. Okay, and then we cannot have t, right? So this is the y-axis, this is the t-axis. So t cannot be pi k, where k is an integer. So that's, if you haven't seen this, this is z stands for integers. Integers are the counting numbers and the negative counting numbers in 0. So you've got 1, 2, 3, 4, 5, 0, -1, -2, -3, -4, and so on. And so this is saying that we cannot have 0. Right, 0 is an integer, and then we cannot have, so this is, t cannot be pi k, so we need to put, it's not 1 on there, it's pi. So maybe let's extend it over here. So we can't have pi, 2 pi, 3 pi, -pi, and so on, right? And so we can put dash lines there, so that cannot be in our initial condition, cannot contain that, because that's where the functions are discontinuous. So we're looking for regions where both f and partial of f are both continuous. So the regions would be the regions that where we don't touch the dashed lines. So if you're going to go through, you'd say it's this region. Oh, that didn't get very close there. You could say this region, right? Here, 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 right? So these are the regions that you could say where you'd have continuity for both f and partial of f, and so on and so on. Okay, and so that explains how to go through and use the general existence and uniqueness theorem. Okay, so we've got two theorems. The first one that we discussed was the linear, right? So that's specific to linear. If you go all the way back here to the beginning, right, specific to linear first order equations. And linear first order equations are the type that can be solved using the integrating factor technique. And so we see that there's conditions on when those would have solutions that exist and are unique. And then we also have our general first order equations, and that's going to cover separable differential equations that are not linear, right? So we have covered multiple techniques of going through and solving differential equations. And so this second theorem would cover anything that's not linear, as you could go through and use the second theorem. Okay, so that concludes the video on existence and uniqueness for first order differential equations. Thank you for watching, and I'll see you next time.